All right, let's talk about something that could completely change the way we think about power, the microgrid. I mean, imagine a world where your lights stay on even when the main grid for the entire city goes dark. That's the whole idea here, creating these small, local power networks that can actually stand on their own.
Seriously, think about the last time the power went out. That flicker, the sudden weird silence, and then the frantic search for flashlights. It's this universal feeling of being totally powerless, right? But what if it didn't have to be that way? What if your local hospital or the fire station down the street could just keep on running, no problem? Well, that's the core promise of a microgrid.
Okay, so what is a microgrid really? To get it, we need to look at the official blueprint. And I want to be clear, this is so much more than just a backup generator kicking on. It's a way smarter system that can create its own little power island.
Now, I know this looks a little dense, but this definition from the IEEE, and these are the folks who literally write the rules for this stuff, has all the key ingredients. Let's break it down. Basically, a microgrid is a local team of power users and power sources, like solar panels or big batteries. It has a very clear border, and here's the most important part. It can act as a single unit that can either be connected to the main grid or, and this is the cool part, disconnect and run all by itself. That's what we call island mode.
And this diagram, it lays it all out perfectly. Let's take a quick tour. So way over on the left, that's the main utility grid. That connection point, the POI, think of it like a drawbridge. Now everything inside that dotted line, that's the microgrid's territory. And in there, you have everything you need to be self-sufficient. Your own power generation like solar, energy storage like batteries, and the loads, which is just a fancy word for the buildings actually using the power. And the thing tying it all together, that little box right there, the microgrid control system, that's the brain.
So let's just boil this all down. For something to be a real microgrid, it's got to have these three things, no exceptions. First, those clear electrical borders we just saw. Second, that single smart control system that acts as the brain. And third, and this is crucial, it has to have enough of its own juice to keep the important stuff running when that drawbridge to the main grid goes up.
Okay, let's zoom in on that controller, because honestly, this is the secret sauce. It's the traffic cop for all the electricity. It's constantly deciding, should we use solar power, should we use the battery, or should we just pull from the grid? And most importantly, it decides when it's time to cut ties and go it alone.
Now here's what's so cool. The controller isn't just a simple on-off switch. No way. It's a really sophisticated system with a bunch of different jobs. But for now, we're just going to focus on the two most important ones, because this is where the real magic happens.
And that magic really boils down to two key jobs, transition and dispatch. The transition function is the one that physically operates that drawbridge, connecting or disconnecting from the grid. Simple enough? The dispatch function is the manager, figuring out second by second whether to use solar, charge the batteries, or maybe even sell some extra power back to the utility. And as you can see from those arrows, these two are talking to each other constantly, making decisions on the fly.
So how does this whole island mode thing actually happen? Well, there are basically two ways. First is a planned islanding. Maybe the utility needs to do some maintenance, so the controller gets a heads up, it gets everything balanced, and then just smoothly disconnects. Easy. But the second way, unplanned islanding, that's where it gets intense. Say a storm knocks out a power line. The controller has to react in an instant. It senses the grid is dead, slams that drawbridge shut, and immediately starts shutting down non-essential things to make sure the critical stuff stays on. It's the difference between a carefully planned maneuver and an all-out emergency scramble.
Okay, that's the theory. It all sounds great on paper, right? But does it actually work when the rubber meets the road? Well, to find out, we're going to look at a massive real-world test case from California, where they took these exact engineering blueprints and tried to build them out in the wild.
Through this program called EPIC, the California Energy Commission basically funded 7 completely different microgrid projects. And the goal wasn't just to build them, it was to study them, to see what kind of challenges pop up when you move out of a controlled lab and into the messy, unpredictable real world.
And this captures that whole journey perfectly. On the left, you've got that nice, neat diagram we were just looking at. And on the right, that's the real deal. That's steel and silicon in the ground. That's the solar array at the Blue Lake Rancheria, one of the actual project sites. This is where theory slams into reality.
So what was the final report card? How did this grand experiment turn out? Well, the CEC's report on these projects gives us this incredible on-the-ground look at the wins, the losses, and all the tough lessons they learned along the way.
And they really put this tech
to the test. I mean, look at this list. They didn't just pick easy sites. We're talking about everything from critical facilities like fire stations and a hospital, all the way to a community college and even an entire remote town out in the desert. This variety was absolutely essential to see how this technology holds up in all sorts of different situations.
So what kind of difference did it make? Well, just listen to this quote from the Blue Lake Rancheria, a tribal nation in an area with a high risk for tsunamis. For them, this wasn't just some cool tech experiment, it was a literal lifeline. It secured not just their electricity, but their water, their food, and their communication systems in an emergency. I mean, that's a powerful statement about what this technology can do.
But it wasn't all a success story. The report found one massive roadblock that came up over and over again: simply getting permission from the utility to connect to the grid. Just look at these timelines. Some of these projects took years. The Bush project took nearly 3 years just to get interconnected. This red tape turned out to be one of the biggest hurdles of all.
I'll let that number sink in for a second. The average time it took to get the green light to connect was over 17 months. That's not building time, that's waiting time. It's a huge delay, and it shows that sometimes the technology is ready to go, but the regulatory side of things is still years behind.
But here's the flip side. Once they were up and running, did they actually work when it counted? The answer is a resounding yes. This chart shows what happened during islanding tests. Blue Lake Rancheria ran on its own for an hour during a real outage. The Fremont fire stations? 6 hours, completely disconnected. The systems worked. They proved the concept.
And let's take a closer look at the Fremont fire stations because it's a great example. They already had diesel generators, right? That's standard for a fire station. But the microgrid adds a solar carport and a battery system. So now, during a big disaster, they can run on sun and battery power first, which means their precious diesel fuel supply will last way, way longer. It's not about replacing the old system, it's about making it stronger.
Okay, so let's step back and look at the big picture here. After digging into the technical blueprint and the real-world report card, what's the verdict? Is the future of our power grid actually local? Well, the answer isn't a simple yes or no. There's this real tension between what's possible and what's practical right now. And this slide really sums up that dilemma perfectly. On the one hand, the promise is huge. We're talking incredible resilience, an easy way to bring in more renewables like solar, and giving communities more control over their own power. But on the other hand, the real-world hurdles are serious. That crazy long interconnection process is a major barrier. The report also pointed out that there aren't a lot of standardized parts yet, so every project is a custom job, which makes it more expensive. And of course, the upfront cost is still a big challenge for a lot of folks.
And that really leaves us with the final question, the one that goes way beyond the engineering and the spreadsheets. It's a question of value. We can calculate the cost of solar panels and batteries, sure, but what's the value of knowing the lights will stay on at the hospital? What's it worth to know the fire station can keep responding no matter what happens to the grid? As we face bigger storms and an older power infrastructure, that's a question every single community is going to have to answer for itself.